Okay, so one-sided limits. Okay, we've kind of already been talking about this idea about approaching a limit from a left-hand side or right-hand side. Now we're going to officially hit it. Okay. Ooh, that was loud. Okay, the limits, or the limit from the right, okay, means x approaches c from values greater than or less than c.
From the right, greater than.
From the right would be from values, greater than c. Okay, so limits from the right, or limit from the right means x approaches c from values greater than c only, okay? And the way we denote that is, you see again, the limit as x approaches c, and we put a little plus sign in the exponent spot. Okay, so the limit as x approaches c from the right. Actually, I'm going to get rid of that equals L part. We really don't need that. Okay. Likewise, right, the limit then, or similarly, in similar fashion, the limit from the left means x approaches c from values, again, if we're approaching from the left, is that going to be values greater than or less than c? From values, yes, less than c. Okay, and again, the way we denote that is the limit as x approaches c, and we put a negative sign in the exponent. Okay, in the exponent. So be very careful about that. It is very easy for students to get confused with this one especially, okay? Because oftentimes students will see this, and for example, they'll see something like the limit as x approaches 2 from the left of the function, and they read this as a -2, and they just they just direct substitute in -2. Okay, so do not do that. Okay, so once again, this says the limit as x approaches +2 from the left of the function. Okay, so what kind of numbers could we use to approximate 2 from the left? What kind of numbers could we use there?
1.999.
1.9, 1.99, 1.999, exactly right. Okay, that's what this is. This is not the limit as x approaches -2. Okay, that's not that. We're approaching 2 from the left, so be careful with that. It's very easy for students to get that confused. Okay, so let's see here. We're going to then, let's do some examples. We're going to evaluate. Okay, so first one here we'll do is the limit
So can we just plug in 3, or do we have to plug in 2.999?
So we'll get to that. Let me just get this real quick here. So Caleb, what is this saying? The limit as x approaches what? 3 from the left. Good. Okay, so yeah, how can we do that? Well, we can use our table on our calculator. That's one option here. So let's go ahead and go to our calculators. Try not to drop them, although they do handle falls okay. They do have, yes, they are kind of designed to resist some shock. Okay, so to mimic or to, you know, approach 3, to mimic kind of approaching 3 from the left, positive 3 from the left, okay, what kind of number should we type in here?
2.9.
Yeah, so I'll do like 2.9, 2.99, 2.999, 2.99999999999. Okay, and what do we end up with here?
0.99. I keep getting 0.997, but you know.
I would give you a battery.
One. Yeah.
So it looks like we go to 1, okay? And in fact, my calculator, right, it reads here, after I type in 2 point with a bunch of 9s, it just gives up and says 3, and then it just gives up and says 1. But if you actually highlight the 1, with your arrow key, right, highlight it, it actually is like really 0.999999997. And of course, so it looks like the closer we get to 3 from the left, the closer we get to positive 1, so we'll go ahead and say the answer here is 1. Okay, now what other option do we have here besides using our graphing calculator? What else could we have done? We could have graphed it and checked it that way. We also could just direct substitute too, right? Direct substitution, 3 squared is 9, minus 3 times 3 is 9, so 9 minus 9 is 0, plus 1 is 1.
Okay, so I don't know if you've like gotten there yet, but really, what's the difference between it just being?
Well, we're working our way there.
Okay.
So we'll get there. We'll get there too.
But there will be like a difference.
Oh yeah. Mm-hmm.
Okay.
All right, next one. Yeah. Okay, so let's see here. So Brandon, what's this? The limit as x approaches what? 1 from the left. Good. X squared minus 5. This is going to be a piecewise function.
Oh, golly.
I know we love these, don't we?
I love you.
You will learn to love them in time. Okay. Shh. Okay. It does kind of look like a 4 there, yeah, sorry. So, in this case, okay, we can kind of use our graphing calculators, but it's better to, let's just go ahead and just look at this. So, Drew, how should we go about evaluating this? Ideas here. Okay, so where should we substitute it, though?
X squared minus 5.
Why there?
X is less than 1, so it's approaching the left.
So, right, we are approaching 1 from the left-hand side. Since we are approaching 1 from the left-hand side, that means we're approaching from values less than 1, so we want to use this top function. And we're going to direct substitute in what number? 1. Yeah, we're just going to plug in 1. So this is equal to 1 squared minus 5, so that gives me negative 4. Okay? Now, that's a little bit uncomfortable maybe for some of us, because when we see we're approaching 1, okay, what are we doing? We're plugging in the number 1. So some of us maybe feel a little uncomfortable because it's like, wait a minute, if we're plugging in 1, that's kind of like equals to 1. Shouldn't we use the bottom one? And the answer is yes. If we were actually evaluating f of 1, so if I wanted to find f of 1, if I wanted to find the exact value of the function at 1, I would use this bottom piece. But I'm not trying to find the exact value of the function at 1. I am approaching 1, and specifically I'm approaching 1 from the left-hand side, which means I need to approach from values less than 1. Where do I go for values less than 1? This top part. So Drew, you're exactly right. We want to use this top one, and then we can use the direct substitution of plugging in the 1 to get the limit. Okay? So that's why that's negative 4. Okay? F of 1, if I want to find f of 1, I plug the 1 in here. 2 times 1 plus 5. Okay, which would be 7. Alright. So there you go. We'll do one more here, and I'll let you guys try this one. The limit as x approaches...
13. Oh, wonder.
So Joey, what's this one say? Limit as x approaches what?
1 from the right side.
1 from the right side. Correct. So it's basically it's the same piecewise function, it's just a different limit. That's all. So. So take 2 seconds there and get that, if you would please. Okay, so let's go to Emma. What'd you come up with? -4 for letter C? Which one did you plug the 1 into? Why? Oh, okay. So why should we use the bottom one here, Emma? Not just because it's equal to 1. Remember, we're a limit. We are approaching 1. From what side are we approaching 1 here, Emma? From the right-hand side. That means values greater than 1. So we want to use the bottom one because this has x values greater than 1. Okay. So 7. Okay. 7. And you're good on that now? All right. Any questions then on that? Okay, that's like the approaching from the left-hand side, right-hand side. Okay. So then we're going to talk about, now that we have that left-hand side, right-hand side, we can talk about the existence, okay, of a limit. Okay. And this is important too, all right? It's not quite as important as like the continuity definition, but it's something we should definitely should know. Okay? Let f be a function and let C and capital L be real numbers. Okay, so again, remember, f is our generic variable or letter that we use to represent a generic function, right? C is kind of like the generic variable that we use in calculus for, like, you know, just a number. And then capital L is kind of like our generic letter we use when we're talking about a limit, like what a limit approaches, okay? Like the answer to a limit problem. Okay, so that's basically what we're setting up here. We're going to be talking about a function that probably approaches some value that where x is approaching c, and it's going to be equal to some limit. Okay, that's kind of like the heads up there. So we're just like kind of declaring those variables. If you guys ever do programming, this is something you do actually in programming a lot too, is you declare variables at the very beginning and then do things with those variables. So if you ever get to programming, you'll see something similar to that. So the limit, okay, of f of x as x approaches c is L if and only if, or IFF, right, if you want to abbreviate. Okay, IFF, that's the abbreviation for if and only if. Okay, so the limit of f of x as x approaches c is L, equals L, if and only if the limit as x approaches c from the left of f of x is the same, well, is equal to L, which is also then equal to the limit as x approaches c from the right of f of x. Okay? So the left-hand limit and the right-hand limit both must be equal to the same number, L. We say the limit then, the continuity, or sorry, the limit exists if the left-hand limit and the right-hand limit agree. Okay? So there's like two main ways for a limit to not exist. This case, okay, the limit of the function from the left and the limit from the right must agree. Okay, so that's one way for the limit to exist. So I guess I should say the limit could not exist if the left hand and the right hand do not agree. So that's one way a limit could not exist if the left hand and the right hand do not agree. And what's the other way that a limit does not exist? You know, Ryan? When they go to infinity, right? Because infinity has no limit; it keeps going. Okay, the idea of a limit is it stops, like it's this value. So going to infinity is not. It means the limit does not exist. or if the left-hand or the right-hand limit do not exist. And there's one more way that a limit cannot exist, and it's kind of the weird one that you really never really see.
What is it? Undulate?
Oscillate is the word, right? That weird sine of x, what was it? Sine of x over x, I think, and it's just like it vibrates real quick back and forth.
Like a swimmer.
We're getting to that later. We're going to later. Yep. Yep. We will be though, for sure. Now that's different though. So that's taking the limit as x approaches infinity. So like you can still do a limit of that. It's just that a limit should never equal infinity. If it does equal infinity, then you say it does not exist, or negative infinity too. So yeah, we'll do that for sure. Okay. So here we're going to do this. Determine the intervals.
More notes or examples.
These are examples. Determine the intervals on which each function is continuous. Okay, so these are examples, sorry, so example. Determine the intervals, and I should put the S in parentheses because there might be more than one, there might only be one. So determine the interval or intervals on which each function is continuous. Okie dokie. Artichoke. So we'll do two. Alright, so we'll talk about g of x. And g of x is piecewise. Piecewise, I think, are used quite a bit because they have such, they're easier to write, and they have interesting kind of continuity behaviors and things. So, well, you might not find them interesting, but anyway, you can come up with all sorts of fun little continuities and things.
Easy to manipulate. Yeah.
Okay. So this is a question that I don't think we've really talked about, right? Determining the intervals on which a function is continuous, like determining when a function is, like describing, okay, the function is continuous from here to here, and from here to here, and from here to here, something like that. I don't think we've really talked about that, okay? But we go about this in a very similar fashion to how we do domain, okay? Because when you talk about domain, right, you're trying to talk about all the x values that work in the function, right? Here in this case, it's the same thing. We're going to start assuming that it's continuous everywhere, and then try to look for places where it's not continuous. Okay? So, when you have a piecewise function, we have to look at the pieces, and then we have to look also at the big picture overall. Okay? So let's look at the individual pieces here. 2x minus 1 for x values less than 0. 2x minus 1, we know that's going to be the graph of a what? It's going to be a linear equation, it's a line, right? And so, will a line ever be discontinuous for x values less than 0?
No.
The answer is right. So at 0, we'll worry about that later. But less than 0, no, we're fine. Any value less than 0 we plug in here, no problem. Okay? And again, this is like what you guys will be going through here. So we look at the first piece and say, okay, this is never discontinuous for x values less than 0, we're good. Okay, what about the second piece? What about the bottom part of this function? Is e to the x plus 1 ever discontinuous, or is there any really ever trouble for x values greater than or equal to 0? So if it goes to infinity, but again, like just for any individual number, any number you plug in, will there be a problem? No, we're fine. E to the x plus 1, no problem. And so the individual pieces are continuous everywhere for their respective intervals. So where is the only other place this thing could be discontinuous?
0.
At 0, because what could happen at 0?
You could approach two different points.
We could have a disagreement, right? This here is like the left-hand part of our graph, and it could disagree with the right-hand part. So what we need to do here is essentially look at the kind of like left-hand and right-hand limits, okay? So the limit as x approaches 0 from the left, and I'll just put in g rather than doing the thing here, okay? As we approach 0 from the left, that means our top piece here, okay? What's the value as we approach 0 from the left in our top piece? It's going to be -1, right? We tried direct substitution. 2 times 0 is 0, minus 1 is -1. So as we approach 0 from the left, our function goes to -1, a y value of -1. Okay, so now let's see if the right-hand side will match up and join with that left-hand side. So as we approach 0 from the right,
2.
okay, we plug 0 in. E to the 0 is 1. 1 plus 1 is 2. Okay, so do these join up? No, they do not. So where is this continuous? What are the intervals? Well, we're going to start at negative infinity, and then go to what? 0, because that's our point of discontinuity, and then close that parenthesis. And that's it, right?
No.
No, we got to keep going, right? Union. Where do we start now?
0.
0 to infinity. That's right. Okay.
So there will be no brackets at all in this, because even though 0 is defined for my approaching from the right.
There are no brackets, correct, because, again, we're talking about continuity, not domain restrictions. So the domain for this would be all real numbers. Domain is all real numbers, but the continuity, so we could say, like, continuous on, and then this interval right there, okay? But the domain would be all real numbers, negative infinity to infinity. Okay, let's try another one here. And then I'll show you guys, have I shown you how to graph piecewise functions yet? I have? All right, well, we'll take a look at them on our calculators anyway, because I feel like some of us could probably use more practice with that too. So we'll take a look at them on our calculators. Okay, and then we'll probably call it a day. Yeah. Well, I mean, we'll do homework. I mean, we're not going to just sit and, watch movies, but,
Why not both?
Why not both? Why not both?
Like
We'll see.
El Paso commercial.
Yeah, exactly. All right, so we're going to do another piecewise. We'll have x squared minus 1 over x minus 1. And that's going to be for x values not equal to 1. And then we'll say it's 4 for x equal to 1. Oh, does this conflict with AP Computer Science?
No. AP Physics.
Oh, okay.
And AP Physics is more important.
Yeah, that's why I'm not taking history classes here.
I have AP US next semester.
Okay.
Right.
Right, so now you're,
When do you have AP?
All right, folks, so here we go. So there's our function. So now let's, again, analyze this, okay? So, again, we look at the individual pieces first. So the top part. Is this top part ever discontinuous?
At 1.
At 1, but the good news is, that's when we don't equal 1 ever. So any other x value besides 1, is this continuous? The answer is, yeah, it is. It's fine, okay? It's going to be good, okay? And then here, this is just 4, x equals 1. So the biggest thing is, where is the only place then where it could be potentially discontinuous? At 1, right, where it switches. So we have to check to see what is the value of this function, okay, as we approach 1. So what we can actually do is just take the limit overall, since we're not really this is just x not equal to 1, so we can actually just approach 1 overall. Okay, because there's no real left-hand part, right-hand part here. It's just not equal to 1, so that is kind of left and right. Okay, so just take the limit as x approaches 1 of h of x. Okay, which is equal to then, if we try direct substitution here, we get 0 over 0. But we can factor and cancel, right? So let me hold off on that. So it's going to be equal to the limit as x approaches 1 of x minus 1 times x plus 1. Oh, sorry. Thank you, Anna. Okay. So we're going to evaluate this limit, but again, to evaluate it, we have to do some cancellation first. So this is one of our strategies, one of our techniques we have. So those cancel. Its limit as x approaches 1 of x plus 1. Okay, and now what can we do? Direct substitute, we get a 2. Okay, great, we got an answer. So now what? What does that mean? So is the function going to be continuous at 1? Drew? Yeah, no, right? Our y value as we approach 1 is 2. Our y value as we equal 1, when we equal 1, is 4. Okay? So that means we're going to have our nice graph, and they're going to have a point, okay, that's off the graph there, and so it's not going to be continuous. So it's continuous on the interval from negative infinity to 1, right, because we're talking about x values here, union 1 then to infinity. Okay, because we have a problem at 1. All right. All right, so let's graph one of these here. Let's graph this this first one, okay, just to make sure we know how to graph that. We can graph piecewise functions on our calculator. So yeah, we'll graph these on our calculator. Brittany, have you guys graphed? Okay, great. So I'm going to show you how to do this. It's really handy because it'll let you be able to analyze, graph piecewise. I mean, you should be able to graph it by hand, but it helps in the calculator. So here's how we do that. Okay, so you break the piecewise function up into its parts, and you graph each part, y1, y2, y3. So here we have 2 parts, so we'll have 1 in y1, 1 in y2. So we'll do 2x minus 1, and put your part in parentheses, okay, like that. So 2x minus 1. And then we're going to do something a little bit weird. We're going to write divide, and then parentheses. Okay, and we're going to divide by our argument, x less than 0. Okay, so this is going to be like, all right, this is telling us we're only going to graph for x less than 0. So we're going to write that, x, the less than symbol, okay, where is that? Do you guys remember? Second math button, which is get you the test menu, and they can see your less than, greater than, equal to, not equal to symbol. So there's the less than. Okay, and then type in 0 and close that and hit enter. Okay, and then we'll do the other piece. Again, parenthesis e to the x plus 1 divided by parenthesis x, and then now math, second math, greater than or equal to 0. Like so. Okay, and then we graph it, right? And voila. Okay. You can clearly see here that we have a discontinuity, right, at x equals 0. All right. So, bringing in summary here, what's happening? How this works is your graphing calculator, it's got this to graph, so it graphs it like it normally would. But the thing is, this division, what this divide by does is x less than 0, that returns it's kind of like a binary thing. It's like basically it returns a 1 if it's true. So for every x value that's less than 0, it returns a 1. So this thing then graphs. If this thing is false, it returns a 0, which then divides that by 0, which means your calculator won't graph it because it's undefined then, okay? Same thing is true for that, so that's how it kind of works. Okay, it's a little bit of a programmer-y kind of thing. Okay, so Mac, what kind of discontinuity do you see here? Is this a removable or a non-removable discontinuity? Can we fix it? So it's non-removable because it's got a jump there. Non-removable. Okay? Other questions on that? Rock and roll. So I'm going to give you guys 2 things here. We're going to have an assignment from the book.